In one of the most remote and hostile places on Earth, something is happening that scientists have been watching for years, almost afraid to see it arrive. Antarctica's Thwaites Glacier, widely known as the Doomsday Glacier, is about to lose the one feature that has been slowing its retreat. And according to the researchers tracking it closely, this is not a distant future scenario. It is happening now. To understand why that matters, start with the glacier itself. Thwaites is enormous, roughly the size of Florida. In some places, it is more than 6,500 feet thick, and at its widest point, it stretches about 75 miles across, making it one of the widest glaciers on Earth. But its size alone is not what makes it dangerous. Thwaites matters because it acts as a structural pillar for a much larger section of the West Antarctic ice sheet, holding back ice that could eventually flow toward the ocean. Scientists have been studying Thwaites through a dedicated international research effort since 2018, when the International Thwaites Glacier Collaboration, a joint program involving American and British researchers, was launched. Funding a multi-year, multi-million-dollar campaign focused on one glacier shows how seriously the scientific community already viewed the situation, even before the latest alarming headlines began. Since that collaboration started, researchers have used tools rarely combined at this scale. They have deployed autonomous underwater vehicles, ice-breaking ships capable of moving through some of the thickest sea ice on Earth, and networks of GPS sensors anchored directly to the glacier. These instruments track the ice's movement in real time and help scientists understand what is happening, not only on the surface, but also beneath the glacier and along the ocean floor. Think of Thwaites less like a single glacier and more like a cork in a bottle. Behind it sits enough frozen ice to raise global sea levels by roughly 10 feet if the broader West Antarctic ice sheet were ever to fully destabilize. Thwaites itself, if it disappeared entirely, would add a little more than 2 feet to global sea levels. But the greater danger is what could happen behind it if the glacier loses its ability to restrain the ice farther inland. Even a fraction of that potential rise would fundamentally reshape coastlines around the world. Low-lying cities, such as Miami and London, along with communities across Bangladesh and the Pacific Islands, are already dealing with smaller increases in sea level caused by melting ice and warming oceans. A rise measured in feet rather than inches would push storm surges, high tides, and routine flooding far beyond what existing coastal infrastructure was designed to handle. Governments would face difficult decisions about seawalls, relocation, and which communities could realistically remain protected. For years, Thwaites has had a natural break system slowing this process, a floating extension of ice called the Eastern Ice Shelf. It sits at the glacier's mouth, where the ice reaches the ocean. Part of the shelf rests against a raised ridge on the seafloor, allowing it to act like a doorstop. As long as it remained stable, the shelf restrained the ice flowing outward from the grounded glacier behind it. Understanding the difference between a glacier and an ice shelf helps explain why its loss matters. Thwaites begins on land, where gravity slowly pulls the thick ice toward the coast. But as the glacier extends over the ocean, part of it moves beyond the underlying bedrock and begins floating. That floating section remains connected to the grounded ice behind it, which allows it to push back against the outward flow. Remove that brace, and the grounded ice loses much of the resistance that had been slowing its movement. That buffer is now breaking apart. Robert Larder, a marine geophysicist with the British Antarctic Survey and coordinator of the UK side of the International Thwaites Glacier Collaboration, has said the remaining ice shelf is very likely to disintegrate before the end of this year. Satellite imagery already shows the shelf fracturing in the locations researchers were most concerned about, where it anchors against the underwater ridge and along the front edge where it connects with the glacier. Christian Wild, a geophysicist at the University of Innsbruck, described watching large sections break apart in a pattern resembling a windshield shattering into a spreading web of cracks. Karen Alley, a researcher at the University of Manitoba who studied the same ice in 2019 and 2020, said recent satellite images barely resemble what she remembers seeing only a few years ago. Large gashes have appeared where there were once none. The speed of the change is what has caught scientists off guard. Movement on the western side of the shelf has roughly doubled over the past 8 months, while the flow rate of the shelf itself has nearly tripled. Between January 2020 and January of this year, the ice moved at a rate of just over 2,000 meters per year, a pace several researchers have described as abnormal for a structure of this size. To understand why this is happening, scientists have had to look beneath the glacier, where warm ocean water is attacking it from below. Thwaites rests on bedrock that slopes downward as it extends inland. That shape allows relatively warm seawater to move beneath the glacier and continue melting it from below, even while the surface remains intact. Researchers using ice-breaking ships and an underwater robot called IceFin have confirmed that seawater is traveling more than 6 miles beneath the glacier itself, actively accelerating melting at its base. Icefin is a torpedo-shaped vehicle lowered through boreholes drilled directly through hundreds of meters of ice. Once it reaches the water beneath the glacier, it navigates autonomously through the freezing environment, recording temperature, salinity, and current speed while capturing video of the underside of the ice. Sending equipment into this under-ice environment carries genuine risk. If the robot fails far below the surface, there may be no practical way to retrieve it. Icefin is connected to the surface team by a thin communications cable, but the vehicle operates far beyond the reach of physical assistance. The data it has gathered represents some of the only direct, close-range observations scientists have of how warm water interacts with the ice at the exact boundary where melting occurs. Satellite observations are essential, but they cannot provide that same view beneath the ice. Robert Larder has emphasized that the warm water moving toward Thwaites is not simply the result of the ocean becoming warmer in a uniform way. The larger issue is changing ocean circulation. Shifts in southern hemisphere westerly winds are pushing warmer, saltier water upward from the deep ocean and directing it toward the Antarctic coastline. Those wind changes are part of the broader climate pattern scientists have been tracking around the planet. The timeline matters because headlines about a Doomsday Glacier can make the situation sound more sudden than it is. Losing the eastern ice shelf this year does not mean Thwaites will collapse next year, or even within the next decade. A structure this large will take far longer to fully disintegrate. Researchers expect any full-scale collapse to unfold over centuries, not years. What losing the ice shelf means is that one of the mechanisms slowing the glacier's retreat is being removed. Without that restraint, Thwaites could retreat and lose ice more quickly than it has already been doing. That distinction is important because some of the most extreme scenarios once discussed now appear less likely than scientists originally feared. One of those scenarios involves marine ice cliff instability. Under this theory, increasingly tall and unstable ice cliffs collapse in a runaway chain reaction. As more ice breaks away, taller cliffs are exposed behind it, creating a cycle of repeated failure. Computer modeling published in 2024 suggested that Thwaites may not be as vulnerable to this specific mechanism as once believed, although researchers have cautioned that more work is required before the possibility can be ruled out completely. Even without that most extreme outcome, the more conservative projections remain deeply concerning. One study published in Geophysical Research Letters projected that Thwaites could be losing between 180 and 200 billion tons of ice per year by 2067. Separate research tracking 2 decades of fractures within the eastern ice shelf found that its structural integrity has been weakening through a two-phase pattern. First, long shear fractures expand across the ice. Then, smaller cracks spread throughout the shelf in a rapid increase that further compromises its strength. That study projected that the glacier's baseline retreat rate could approach nearly 1 kilometer per year over the next 4 decades. Hilmar Gudmundsson, a glaciologist at Northumbria University who has spent years modeling Thwaites' possible collapse, described a major change in scientific confidence. Researchers, he said, have moved from genuine uncertainty about whether an unstable, self-reinforcing retreat could occur towards something closer to near certainty that it will eventually happen. That does not mean scientists consider the outcome inevitable in the short term. It does not mean a sudden collapse is scheduled for this year. It means the physical conditions that could allow an unstable retreat are becoming increasingly difficult to dismiss. The central question is the glacier's grounding line, the place where the ice stops resting on the seafloor and begins floating. If that grounding line continues retreating as current trends suggest, more of the glacier becomes exposed to warm water. The retreat can then make further retreat easier, creating a self-reinforcing process. This is where climate policy still matters. Researchers continue to emphasize that reducing global carbon emissions could slow the process, even if it cannot fully reverse changes already underway. The difficulty is that global fossil fuel emissions remain near record levels, with no clear sign of reversing quickly. The decisions made over the next several decades will help determine whether the worst outcomes unfold slowly over centuries or accelerate more rapidly. Climate researchers studying Thwaites are careful to distinguish between changes that may already be locked in and those that remain open to human influence. Some retreat is now likely because the glacier has already moved so far inland and because warm water has reached areas that were previously protected. But the speed of future retreat is not fixed. Continued emissions choices could still meaningfully affect how quickly and how severely the glacier loses ice. There is also a broader concern tied directly to Thwaites' role as a structural pillar for the region. Scientists often compare removing the ice shelf to pulling a goalie late in a hockey game. Once the goalie is gone, the ice behind it can move toward the goal much more freely. In the same way, removing the eastern ice shelf could allow the rest of the glacier to flow toward the ocean with less resistance. The wider West Antarctic ice sheet contains enough frozen water to raise global sea levels by more than 10 feet if it were ever to fully destabilize. That would not happen overnight. and scientists are not predicting a sudden 10-foot rise. But because Thwaites helps restrain part of that larger system, its condition is treated as an early warning indicator for a much wider process. Climate scientists often describe systems like the West Antarctic ice sheet using the concept of a tipping point. This refers to a threshold beyond which change becomes effectively irreversible on any timescale that matters to human civilization, even if the original cause of the change were reversed. Once a large glacier's grounding line retreats past a critical point on unstable, downward-sloping bedrock, the physics of the system can take over. As the grounding line moves inland, the retreat may become progressively easier to sustain even without additional ocean warming. That is why researchers such as Gudmundsson describe the science as shifting from uncertainty toward near certainty about eventual instability. The concern is not only how warm the ocean becomes, it is whether the glacier has already been pushed past a structural threshold from which recovery becomes physically implausible. That does not mean the glacier is about to vanish. It means the system may have entered a phase where the long-term direction is increasingly difficult to change. The difference between a collapse occurring over a few centuries and occurring over many centuries would be enormous for coastal planning, infrastructure, migration, and global adaptation. Researchers stationed in Antarctica this year have described an almost constant state of vigilance while tracking the changes. Scientists check satellite imagery daily to determine how quickly the fractures are spreading. Teams have also worked directly on the ice, attempting to place monitoring equipment beneath the glacier's main trunk to measure water movement, temperature, and flow speed. Even when instrument deployment has not gone exactly as planned, the field teams have confirmed that water moving beneath Thwaites is both warmer and faster flowing than earlier models predicted. That adds another piece of evidence pointing toward an accelerating retreat rather than a slowing one. Working in this environment creates challenges far beyond the scientific questions. Field teams operate in one of the most logistically difficult regions on Earth. They may fly aboard specially equipped aircraft capable of landing directly on ice runways, then live in temporary camps where temperatures drop far below anything most people ever experience. The terrain is also dangerous. Researchers must transport equipment across surfaces cut by crevasses, where the ice shifts and cracks beneath their feet. Drilling access holes through hundreds of meters of ice can take days of careful, physically demanding work. The crews must complete those operations within a narrow weather window before conditions become too hazardous to continue. Every successful measurement gathered under these conditions represents a logistical achievement in addition to a scientific one. It is one reason researchers describe each field season at Thwaites as both scientifically vital and physically punishing. The underwater robot ice fin has been especially important because it allows scientists to observe the underside of the ice directly. A satellite can show the glacier's movement and surface fractures, but only an instrument below the ice can reveal how warm water reaches the grounding zone, how fast it flows, and how the melting geometry is changing. Those details matter because the way a glacier melts can be as important as the total amount of ice it loses. A broad, shallow melt pattern may behave differently from a narrow channel that carries warm water deep beneath the ice. Scientists are still working to understand the complex pathways that allow ocean water to penetrate beneath Thwaites. The glacier's retreat may also have begun earlier than once believed. Research tracing the history of its movement suggests that the decline began as far back as the 1940s, possibly after a powerful El Niño event altered ocean conditions along the Antarctic coast. If correct, that means the current retreat has been unfolding for roughly 80 years, even though modern observations have only captured a small part of the process. That history is important because it shows that Thwaites is not responding to one isolated event. It is reacting to a changing ocean, changing winds, and a long-term shift in the balance between ice flow and ice loss. The eastern ice shelf is the latest visible expression of that deeper process. The immediate concern is what happens once the eastern ice shelf breaks apart. Researchers do not expect the entire glacier to collapse suddenly. Instead, the shelf's disappearance will remove resistance from the front of the system, allowing the grounded ice to accelerate and the grounding line to retreat more easily. The exact response will depend on the shape of the seafloor, the speed of ocean currents, the distribution of fractures, and the geometry of the glacier's retreat. Some areas may accelerate quickly, while others may respond more slowly. That uncertainty is one reason scientists are monitoring the region so intensely. Satellite observations provide the broad view. Radar measurements reveal how quickly the ice is moving, while optical imagery shows the spread of cracks and changes in the shelf structure. GPS stations anchored to the ice provide local measurements of flow, speed, and direction. Oceanographic instruments record temperature and salinity beneath the floating ice, helping researchers identify where warm water is entering the system. Together, these observations create a detailed picture of a glacier under pressure. The images showing the shelf shattering are dramatic, but the most important evidence may be less visible. The grounding line retreating, the ice speeding up, and warm water reaching farther beneath the glacier than expected. The challenge for scientists is to connect all of those measurements into a reliable model of future behavior. Glaciers are complicated systems. Their movement is affected by gravity, friction, ocean tides, water pressure, ice deformation, seafloor topography, and atmospheric conditions. A small change in one part of the system can alter the balance elsewhere. For example, meltwater created beneath the glacier can act as a lubricant, reducing friction between the ice and the bedrock. That may increase the glacier's speed and send more ice toward the ocean. At the same time, fractures can weaken the ice shelf, making it less able to resist the pressure from behind. The resulting feedback can accelerate both structural failure and ice loss. However, not every feedback produces runaway collapse. Some processes can slow the retreat. Sediment deposited beneath the glacier may create temporary ridges that stabilize the grounding line. Changes in ocean circulation may reduce the amount of warm water reaching the ice. Increased snowfall could add mass to the surface, although current snowfall is not enough to offset the losses in the most vulnerable areas. That is why scientists use a range of scenarios rather than a single prediction. The goal is not to announce a precise collapse date, but to estimate how the glacier could behave under different emissions and ocean conditions. Each new field measurement helps narrow those possibilities. Some of the most severe scenarios once discussed have become less likely. The marine ice cliff instability mechanism, for example, may not produce the runaway collapse originally feared. But ruling out one extreme mechanism does not make the situation safe. A slower, more predictable retreat can still generate major sea level rise over centuries. That longer timeline can be difficult to communicate. Centuries may sound distant, but infrastructure decisions made today are designed to last for decades. Roads, ports, airports, housing developments, seawalls, and drainage systems built now may still be operating when Thwaites is contributing substantially more to sea level rise. Coastal communities need planning horizons longer than a single election cycle. They must consider whether it makes more sense to protect existing neighborhoods, redesign infrastructure, restrict new development, or begin planned relocation. These decisions become more difficult when future sea level rise is uncertain, but uncertainty is not the same as safety. The loss of the eastern ice shelf may therefore become an important marker in the glacier's history. It will not be the moment when global coastlines suddenly change. It will be the moment when one of Thwaites' main restraints disappears, increasing the likelihood of faster retreat and giving scientists a new phase of the process to study. That is why the breakup is being watched so closely. Every fracture, every change in flow speed, and every movement of the grounding line provides information about how an ice sheet responds when a major buttress is removed. The observations could improve projections not only for Thwaites, but also for other glaciers with similar geometry around Antarctica and Greenland. The stakes are global, but the process is remote and slow. There will be no single day when scientists can say that the entire West Antarctic ice sheet has passed a final point of no return. Instead, evidence will accumulate through decades of measurements, gradually revealing whether the system is stabilizing, accelerating, or moving toward irreversible retreat. For the people living far from Antarctica, the effects of Thwaites' retreat may seem abstract. The glacier is thousands of miles from the cities most exposed to sea level rise, and the changes beneath its ice are difficult to see. But the consequences are tied directly to decisions being made today. A small increase in average sea level can make a major difference during storms. Higher baseline water levels allow storm surges to travel farther inland. High tides flood streets that previously remained dry. Drainage systems lose capacity because they are trying to move water into an ocean that is already higher. Over time, flooding that was once considered rare can become routine. As Thwaites loses more ice, it will add to the sea level rise already caused by thermal expansion and the melting of glaciers and ice sheets elsewhere. The contribution from Thwaites will not arrive as a single wave. It will accumulate gradually, increasing the pressure on coastal communities to adapt. The most important scientific question is not simply whether Thwaites will retreat. It is how quickly. A slower retreat gives cities more time to plan, finance, and build defenses. A faster retreat compresses those decisions into a shorter window and increases the chance that communities will be forced into emergency responses rather than deliberate adaptation. That is why emissions reductions still matter, even if some instability is already likely. Cutting emissions cannot instantly rebuild the ice shelf or move the grounding line back to where it was, but it can slow ocean warming, reduce the duration of dangerous conditions, and lower the amount of ice ultimately lost. The difference between moderate and extreme future warming could translate into many feet of eventual sea level rise and vastly different costs for coastal societies. Researchers are careful not to frame this as a simple choice between saving Thwaites and losing it. The glacier is responding to conditions that have already changed, and some future loss is likely. The realistic goal is to influence the speed and scale of that loss, preserving as much time and stability as possible. The scientific community is also improving its ability to observe Antarctica. Satellite missions now measure ice elevation, surface velocity, fractures, and grounding line movement with remarkable precision. Autonomous underwater vehicles can explore areas that were previously inaccessible. Ocean sensors track the temperature and direction of water beneath floating ice shelves. These systems are essential because Antarctica is difficult to visit frequently. Field seasons are short, weather can interrupt operations, and the region is too large for direct human observation alone. Satellites provide continuous coverage, while field teams supply the detailed measurements needed to interpret what the images mean. The data from Thwaites is also helping scientists refine models of other vulnerable glaciers. Pine Island Glacier, located nearby, faces related risks from warm ocean water and retreating grounding lines. Across Antarctica, many glaciers sit on bedrock that slopes inland, creating the potential for marine ice sheet instability. Understanding one system helps scientists evaluate the vulnerability of others. The same research has implications for Greenland, where outlet glaciers are also losing mass and responding to warmer ocean water. Although the geography and ice dynamics are different, the basic lesson is similar. Floating ice shelves and grounded glaciers are connected parts of one system, and changes at the ocean boundary can affect the entire flow of ice behind it. For coastal planners, the message is increasingly clear. They should not wait for perfect certainty before beginning adaptation. Sea level rise projections will continue to improve, but infrastructure takes years to design and build. Communities that begin planning early have more options than those that wait until flooding becomes unavoidable. That may include restoring wetlands, redesigning drainage, elevating roads and buildings, strengthening seawalls, revising building codes, and limiting new construction in areas that will become increasingly exposed. In some locations, it may eventually require managed retreat. None of these choices are easy, but delaying them does not remove the risk. It only reduces the time available to respond. Thwaites has therefore become more than a scientific curiosity. It is a test of whether society can respond to a slow-moving crisis before it becomes an emergency. The glacier's fractures are spreading in a remote Antarctic landscape, but the decisions that determine the consequences are being made in cities, legislatures, and communities around the world. Whatever happens to the eastern ice shelf over the coming months, one thing about this story is already clear. The question surrounding Thwaites has genuinely shifted. Scientists are no longer asking only whether an unstable, self-reinforcing retreat is possible. Increasingly, they are asking how the process will unfold, how quickly the glacier will respond, and which parts of the future can still be influenced. That shift does not mean collapse is imminent. It does not mean Thwaites will disappear in a few years, or that global sea levels will suddenly rise by several feet. It means the long-term trajectory has become more concerning as warm water reaches farther beneath the ice, the grounding line retreats, and the eastern ice shelf loses the strength to act as a brake. The most extreme runaway scenarios may be less likely than once feared. But a slower retreat still represents a major threat to coastal communities worldwide. The difference between a rapid and gradual collapse will determine how much time cities have to adapt, how expensive that adaptation becomes, and whether communities can make deliberate choices rather than reacting to repeated disasters. Researchers are continuing to gather every measurement they can. They are tracking fractures from space, mapping the seafloor, measuring the water beneath the glacier, and monitoring changes in ice speed. They are working in dangerous conditions because the observations collected at Thwaites cannot be replaced by models alone. Direct evidence of how warm water reaches and melts the grounding zone is essential for understanding what comes next. The wider lesson is that climate systems rarely fail in one dramatic moment. They shift through a sequence of changes, each one altering the conditions for the next. The weakening of the eastern ice shelf is one step in that sequence. The retreat of the grounding line is another. The acceleration of ice flow and the arrival of warmer water are additional pieces of the same process. Human choices still matter within that process. Reducing emissions will not instantly reverse the changes already underway, but it can slow the retreat and reduce the eventual amount of sea level rise. The decisions made during the next few decades will influence whether future generations inherit a coastline altered gradually over centuries or one forced to adapt much more rapidly. For coastal communities thousands of miles away from Antarctica, the answer to that question is already shaping decisions about seawalls, relocations, drainage systems, and long-term development. The future of those communities is being written partly in the fractures spreading across a remote ice shelf right now. Thwaites is not a doomsday switch that will suddenly destroy the world. It is a warning system, a vast and vulnerable part of the Antarctic ice sheet showing how warming oceans can destabilize ice from below. Its retreat will not happen overnight, but its consequences could continue for generations. The scientists studying it are not predicting a single catastrophic day. They are documenting a process. Every new measurement helps clarify whether the glacier is approaching a threshold, how much of its retreat is already locked in, and how much can still be slowed through global efforts to reduce emissions. That is what makes the current moment so important. The eastern ice shelf may disintegrate before the end of this year, but its loss will be the beginning of a new phase, not the end of the story. The glacier will continue to move, the grounding line will continue to respond, and researchers will continue watching for signs of acceleration or stabilization. If stories about the science behind Earth's changing ice sheets and what they mean for coastal communities matter to you, like this video and subscribe. Thwaites' situation is actively developing, and researchers expect major updates as the ice shelf breakup continues to unfold. The glacier is losing its last natural break, and the scientists watching it happen are doing exactly what they have done for years, gathering every piece of data they can, trying to understand not if this will eventually reshape coastlines around the world, but how quickly and how far that change will ultimately reach.